Now there are a couple of things going on here. One is we scatter a lot of light in our atmosphere so that you're not getting the ultraviolet light down on the ground that you get up in space. The other thing that's happening is you've got nitrogen and oxygen and water molecules and other pollutants absorbing in our atmosphere. And so that's what these gaps are in the solar spectrum. In space, it is roughly 1,367 watts per square meter. On the ground, it is roughly, just on average, about 1,000 watts per square meter. So you've got more sunlight, but you're going to see shortly that you have less of an ability to actually use that sunlight for productive electricity. Now, that was sort of an introduction to the physics of the solar cell, and now I want to go to a little bit more general kind of background for you. The first solar cell was done in Bell Labs. We are very, very sorry that Bell Labs no longer does basic research. That stopped. Things like the transistor and the solar cell came out of that lab. These were the fellows that did it, Pearson, Chapin, and Fuller. And this was the very first solar-powered satellite. Sputnik was battery-powered. It died within 6 hours. They were afraid when they were building this. It was a combined effort by the Navy Research Lab and the Army to actually do this first satellite. They were afraid to use the solar cells as their primary power source, so they put in a battery to run the. Really, it was all it was running was a communications beep, 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 right? And of course, Sputnik didn't last very long. It turned out that the battery didn't last very long either. When they put Vanguard 1 up, it beeped for about 6 days. And then it died. But they had a backup. They had these silicon solar cells, and the thing annoyed the heck out of people, as a matter of fact, beeped on for 6 years on the satellite. And since that day, by the way, have been the power system of choice for satellites in space. There have been a few nuclear-powered satellites, which mostly the Russians did, but there are all of our communications satellites today are powered by solar cells. These cells were crystalline silicon cells made by Hoffman Electronics, which no longer exists. It actually got folded into Hughes, which is now folded into Boeing. So they were about 6% efficient, meaning they turned roughly 6% of the energy of the sunlight hitting the cell into usable electricity. There are really 4 things that should be said about solar today, and the truth is it's real. People are out there, businesses exist, they sell a product, they're being installed, and it will, I believe, firmly believe, play a role in the future of the world, and for good reason. We need to invest both in research and development, but also in policy. We need to put the incentives in place that make this a viable option. By that, I don't necessarily mean that we need to offer up taxpayer money to incentivize people to go out and buy a solar array. What I mean is that if you take the cost of your electricity from your utility and factor in the environmental cost of that electricity, now you've got competition. Coal, most of our power in this country is from coal-fired power plants. If we now are seriously concerned about the amount of carbon dioxide that is being released, we will need to do something about that. That will cost money. If you levelize the playing field, then I think your renewable energy alternatives will play on a level basis with the utility-based electric costs. It is true we need to shorten the time between pulling it out of the laboratory and putting it into manufacturing. And for the last 8 years, as probably everyone in this audience knows, there's been a real dearth of research funding in all arenas. If you look at where the industry sits today, and I'm going to come back to this chart in the end because I'm going to go through it in a little more detail, you find that what you've been looking at mostly, and in fact 85% of the photovoltaics that is supplied to the market today is in crystalline silicon. They had a problem with that. They couldn't find the silicon they need, and we'll come back to that momentarily. What you see, I don't like the word disruptive, but other people use it. If you see different approaches for thin film cells and concentrators, and possibly organics, although there are a number of issues with organic solar cells, and much thinner wafers, and much more efficient silicon, you're looking at somewhere, in an evolutionary process, somewhere between 5 and 15 years. And then I'm involved, particularly in here at NASA, I do quantum dots as an alternative for photovoltaics. And there are multiple avenues of approach that we can take that will play a role in future photovoltaic devices. Well, we need to close the gaps. We said before, we need to go beyond our research and bring it to the consumer. We need to raise our cells, if we can, from where they stand today to closer to their theoretical maximum. And we need prototypes. We need advances in the manufacturing processes that are there. And we need to remember that we don't use a single cell by itself. It's in a module. This is a little about Hoffman Electronics I was talking about earlier. The total amount of power they shipped out of Hoffman Electronics in 1958 was 40 watts. What are we going to do in terms of an energy question? Well, if you look at 2007, we're using worldwide about 14 terawatts of primary energy. If one takes even a rather modest growth in that, remembering that some of our developing countries like India and China will be moving into a more energy consumption kind of environment, we see growths that we will need in the energy needs. So we've got to almost double the energy production in the world in order to meet those needs. Well, how would you do it? Well, you're going to need all of it, basically, to solve the problem. Coal will play a role. We have a lot of coal. There's a lot of coal in the world, okay? It will play a role. The question, of course, is that you really don't want the carbon dioxide that you get from burning the coal. So what are we going to do with it? And that remains a burning research issue. Nuclear will grow. We will have to have it. We will have to have it to meet our needs. And last but not least, I hope renewables should grow significantly over time.